Okay, we're back. We're going to start with this example. It's a Glulam beam. The Glulam beam is supported, simply supported on either end, and the span is 48 feet. The Glulam member has several laminations, so it's pretty deep section, 37.5 inches, and the width of the section is 6 3/4 inch. Okay, this Glulam member is, we're told, it's of the class 24F V5. We'll see shortly in NDS what that means. And it's in the stress class 24F 1.7E. So the 24F, very quickly, is that the reference value, both of these are telling us that the reference value for FBX is 2400 psi, and I'll show you shortly. And then VF5, it's visual grade for V, and the 5 is the combination that we're using for the laminations. And 1.7E, it's also telling us that the reference value is 1.7 times 10 to the 6 psi for the reference value of the Young's modulus for the wood that we're using. Okay, so let's look into IDS to see what each of these things are. So I'll go first, look at the 24F 1.7E. Where is that and what does it imply? Where does it show up on NDS? And then 24V5. And for both of those, we have to go to the NDS supplement. And so for the NDS supplement, now we're looking at table 5A. This is the 2018 version. So it's on page 63 down here. So if we go into this, you're going to see for reference design values for glulams and softwood. Okay, our Douglas fir is a softwood, and the numbers that you see, if it's a 24F 1.7E, boom, here is our 2400 psi reference value. Note that this is the reference value for positive bending. The reference value for negative bending is different, but we're not worried our beam is just going to be loaded in positive bending. It also gives you other numbers: compression perpendicular to grain, shear parallel to grain, and so forth. Here's our modulus of elasticity, and the 1.7E refers to this apparent Young's modulus. That's used only for deflections. If we need to compute any stability, usually for column problems, then any stability problems, we would have to use this E min, which is the 0.9. But for now, what we're really interested in is just understanding this, and it does 24F 1.7E. It's telling us that the reference value is 2400 and that the reference value for the Young's modulus is 1.7. That's the apparent Young's modulus. Okay. All right. So that's the first thing, 24F 1.7E. The second thing that we were told is a 24F V5. So if we go to the next page, page 64, this page is oriented sideways, so it doesn't really help. But if you don't mind, just for a second, looking at this and slanting your head a little bit, here we go for a little bit more information. This is the expanded table 5A for reference design values. And if you go down here, you'll see, boom, here's our 24F number. And now we're told that the combination, the layup, is 24F V5. So 24F V5, sorry, not that one, because it's not SP. What I want is the 24F V5 here, Douglas fir. The positive bending number is 2400, and boom, if I had the negative bending number, then that would be 1600. So it just provides more information, but really what we need now is our 2400 number psi. But I just wanted to go over each of these definitions. Okay, so we're back. Here's our the problem. We just looked at what these 24FV5 and 24F 1.7e meant. To continue this problem, we are going to read the rest of the problem statement. Our beam is, and the loading is being applied under dry conditions and normal temperature. And the load we're going to take from this D plus 0.75 S plus W. And S is for snow, W is for wind. So anytime we have wind loads or earthquake loads, our CD factor is going to be 1.6. We've seen that in our tables before. You guys have done that on the homework. But you can always go back to your load duration table to check this number. But CD is 1.6. We're also going to be assuming that our lateral bracing is sufficient. So that means really that we're going to take CL as 1.0. Okay, and we'll see where that shows up shortly. Okay, so we have a beam, we have a pointed load, we will compute the bending moment shortly, but before we get there, let's look at all the factors that we need. We saw quite a few factors in class, and really when you need to know what factors to use for a bending problem, which this is, then we need to go back to the NDS main book. And in the NDS main book for structural Glulam members, so always when we're looking at structural Glulam, we're looking at chapter 5. So that's Glulams. And table 531 is a really, really good friend. It just says what are the adjustment factors that we should be using. And if we're thinking about bending, which is our problem right now, our reference value, that's the FB, that's the first number that goes in here, reference value, and then FB prime is the adjusted value that we'll be using. So to go from our reference value, and our reference value is the number we looked up the table, which would be 2400 psi in this problem, we need to multiply by all these factors. CD, we've seen that's 1.6, but then we have the West service factor, so the moisture, temperature, stability, volume, this flat use factor, we have a curvature factor, and we have our interaction factor. We need to account for all of these. So I'm actually going to go and plug in, because I'm working with bending, I need to write this whole equation and then go and look at one by one what these factors mean and where do they show up. Okay, so I do have a volume factor, but before that, I'm just going to write here that for our positive bending value, FBX, this would be equal to our reference value in X, right? And then I need to multiply by all of those factors that I just saw on table 531. C sub D, C sub M, C sub T for temperature, our stability factor, and then I have CV volume factor, I have the flat use factor, and curvature, and the interaction. Okay, and we'll have to look at each one of these independently. But that means that if I need the reference value for negative, just to keep track of them, I'll make sure I write positive where it's positive, and I'll write negative for the next one. I do also need the negative reference value here. Okay, and but all of these have to be multiplied by exactly the same factors. Okay, quite a few factors to look at. One of them is the C sub V, and let's start by looking at that one first. So For C sub V, I'll make use of this little space here. That's the one I saw at the end of the previous lecture, which is the C sub V has to do with the reference length. The equation is a pretty long one. I'll write it here for you guys. So it's a function of the length, and the length that we'll be using is the length of the beam. So here for us, the length is 48 feet. Okay. Let me just erase that one. Here we go. And then the next factor has to do with the depth of the beam, and that's always 12 inches. And that one's going to be divided by the depth of the beam. Our depth is right there, 37.5 inches. Okay. And then lastly, we have the width or breadth of our beam. The 5 1/8 is the reference number. That's also in inches. And that's going to be divided by B. I'll draw the B here in green. And B, and that's B right there. Okay. All of these then are multiplied. Sorry, they have an exponent to them, and that depends on it being softwood versus hardwoods. So for the western species, and we'll see what these are here quickly. For the C sub V factor, it's in 536, and it tells us that C sub V, here you are, 21 over L, 12 over D, 521 over B. And for all other species that they're not southern pine, then we use 1 over 10 there for our factor. So 1 over 10, 0.1. I'll actually just go in and say that all of these numbers are going to have an exponent here, which is 0.1, 0.1, 0.1. Once we actually compute it, all of this has to be has to be less or equal to 1.0. So we'll plug in the numbers and see what we get. Okay. So L is 48 feet. I think I'll just have to rewrite it right here. So L, I'm going to switch that number to 48 feet here. And then D, that's the black one. D is black. And for black, I have 37.5 inches. And for B, I'm going to do 6 3/4. So I'm just going to make this line a little bit thinner here, and 6.75 inches. Okay. If you work out this whole thing, all of this, that works out to CV equals 0.8. Okay, so that's our first factor that we're going to be using here. Okay, right, so next, let's just go look at our reference values and work all the numbers that we have here. I'll just move this text a little bit up here. Oh, I dropped the 0.8. I guess that's how I write my 8. Anyway, here's CV 0.8. So FBX. positive. We had seen that that was 2400 for the number that was the reference, but let's look at each of the factors. C sub D, that one is 1.6. I had mentioned that before. Moisture factor, we're using dry conditions, so that's a 1. The temperature, normal temperature, so that factor is also a 1. The stability, and part of the problem statement, we said that C sub L was 1. We just computed C sub V, which is our volume factor. The flat use factor, we are not using the beam rotated, and so it's not being used in the flat use, so that's 1 also. It doesn't have any curvature, and there's no interaction to worry about. So really we have these two, C sub D and C sub V factors to worry about. From the expanded table, the one I had shown you, we saw FBX positive, our reference value in positive bending was 2400 psi. C sub D was 1.6, and C sub V, we just computed it at 0.8. For the negative bending, if you go back to the table, that's 1600 psi, 1.6 for CD, and 0.8 for the C sub V. If you compute those numbers, I get 372 psi, 3072 psi for the positive, and 2048 psi for the negative bending adjusted values. So that's already the prime, the adjusted values here, right? Okay. Right, compression parallel to grain. I'm not going to work on that one. We don't really need it yet. That one. Let's go to the shear parallel to grain. And so shear parallel to grain, that one, the adjusted value is FVX, the reference value for X. But then what we need to go and check is what adjustment factors should I use for this guy. So I go back to this table, 531, and now we're looking at shear. Here is shear in green. And look at that. I only need now these 3 coefficients. All right. And the shear reduction factor, CVR, we'll look at that shortly. But I have the moisture or wet factor, temperature, C sub D, and this new factor, CVR, which is in NDS section 5310. And if you look at 5310, it says the reference shear design values shall be multiplied by a shear reduction factor if you have the design of non-prismatic members, which is not our case, design of members subjected to impact or repetitive cyclic loading, which is not our case, if we have notches or we're designing notches, and if we're designing connections. So CVR for this problem doesn't apply, and here are the cases when it does apply. All right, so we're just going to take that as 1 for our reference, to adjust our reference value to compute our adjusted value. So C sub D, C sub M, C sub T, and CVR. So 1, 2, 3, 4 parameters that I need to make sure I plug in here to the equation. So C sub D, C sub M, C sub T, and CVR. We just saw that one is 1.0. C sub T is 1.0. C sub M is 1.0. C sub D is 1.6. So now we have to use CVX, our reference value. Let's go get that one again. It's in this table. We are working with the 24V5. Here's our 2 reference values, positive and negative bending. And now we're looking for, here we are, 215 PSI as our shear parallel to grain reference value. So 215 PSI. Okay, back here, and 215 psi for reference value in shear, and times 1.6, which is our duration factor, and I get 344 psi as our adjusted shear parallel to grain value. Okay, I'll skip these for now. Again, LRFD is not something that we use often, and so I'll just skip those. All right. So just over 20 minutes, but here we are, an example for a beam, but step by step. So hopefully that helped.